In this video, I'm going to show you a model that you use to estimate project risk costs as well as their estimated probability, and also takes into consideration the cost of the risk response and the estimated reduction in either the cost of the risk itself as a result of the risk response or the reduction in the probability of the risk, and how that would be reduced as a result of the risk response. Because as we know, in project risk management, mitigating risk can take the form of mitigating probability or impact, or even doing both at the same time. So I'm going to walk you through this simple model that uses a PERT estimate, because that is one of the most common forms of distributions in a basic project risk management model. So this is a model that's been set up and is ready to be populated using PERT distributions to estimate risk costs. So I'm just going to quickly explain this model, going through each column, starting with the leftmost column, column A. You will see here on column A, there is a risk name column, which would be something that you would populate based on an existing and already filled out risk register for your project. So you would go and find your risk register and start to determine which risk events you would like to add to this model in at risk, which, by the way, we are using the Palisade at risk function today, which you can see here on the ribbons. This is the Palisade at risk add-in in Excel. So when we add the risks from our risk register and determine which risks we would like to enter in this model, this quantitative risk analysis model, we would want to then look at our risk scores that are included in a risk register that we had created, and then quantify those scores using a PERT-based distribution, meaning that in our estimates, we should have an optimistic risk cost, an expected risk cost, and a pessimistic risk cost. Now, since we were referring to cost in this case, the optimistic risk cost, which can be shown in column B here, would be the lowest cost that an expert or a subject matter expert would believe that risk would cost our project should it occur. The expected cost would be the baseline estimate, or in other words, the mode or the most likely to occur, meaning that in the past, when we've observed similar projects and the risks of those projects when they have occurred, most of the time they end up resulting in a cost which would be reflected in column C. Column D would be the most pessimistic, meaning that would be the most expensive cost that we believe would be the estimate. So in other words, when the risk does occur, what is the worst we've seen from our experience? And if we have no direct experience with that risk cost, we would have to then do some further analysis to use either bottom-up estimating all the way to analogous estimating. But either way, these estimates are strictly cost-based. They're not time-based. So for risk that you've identified does not impact the project in terms of cost, it should not be included in this model. It is only for cost-based risk events. Okay, so column B, C, and D reflect cost estimates based on what would happen to your project if that risk were to actually occur. Column E is a formula, and that is a formula that calculates what appears to be a single point or deterministic estimate. However, you'll notice that the formula uses the risk PERT distribution formula, which means that in reality, these numbers will be randomly selected by the model. So any value between the optimistic, expected, and pessimistic could conceivably be calculated in this cell, which I'll show you in a moment. So even though you will see static values here in column E, in reality, behind the scenes, when we run our model, Excel will select random values amongst this distribution, which we'll look at eventually in this video. Now, your estimated risk probability is another input. This is a deterministic value, meaning that it is a single point estimate based on our estimated risk probability, which would come from, yes, that's right, our risk register and the resulting score. And that score, of course, is based on our scoring system that we would have developed in our risk scales. So we want to be consistent and try to estimate from talking to our SMEs what that risk probability would be. All risks have estimated probabilities, but not all risks have estimated cost impact. It depends on how the risk is perceived to impact the project. From here, column G is the EMV value, the expected monetary value, which is simply the PERT value multiplied by F, which is the estimated risk probability. So probability times impact, in this case, the PERT cost estimate, which appears to be a static number, but in reality, as I said, will be generated randomly based off of the distribution that you see between column B, C, and D. And that will show here in the EMV value. The EMV value then at the bottom is calculated as a total. This EMV value is here only for comparative purposes, because in many projects, project managers use an EMV value to calculate things like how much contingency they should actually have in a contingency fund to cover the cost of project risks. So we will use this to compare against the results of a stochastic model that is seen in this model. So it is for comparison purposes only. Now, column H, here we have another deterministic single point estimate, which is just an estimate of the cost of the risk response. And sometimes that is a very easy cost to be able to determine. For example, purchasing insurance is a deterministic number. It is a deterministic value. There is no distribution in terms of the cost of a insurance plan, because the insurance plan is based on a contract which is fixed. So the cost of risk responses generally is assumed to be deterministic. So single point estimates would come from either contracted values or potentially estimated values from subject matter experts. So you estimate what the cost of the risk response would be, and that could be a very simple estimate, or it could be a more complicated bottom-up estimate. So you enter the cost of the risk response, unless, of course, you are simply accepting the risk. And in that case, there is no risk response. So the estimated cost of the risk response would be, by default, 0. Column I is now a little bit more abstract, and this is estimating the risk response impact cost reduction. In other words, if you have a risk response strategy that would reduce the cost of the risk itself or mitigate the impact of the risk, and that would involve a cost, then you should be determining what you estimate that cost reduction would be. Now, a very important point is that column I should be greater than column H. In other words, what you estimate the risk response will reduce the cost of the risk by must be greater than the cost of the risk response itself. If the cost of the risk is reduced by less than what it would cost you as a project manager to respond to that risk, you should then not respond to the risk and simply allow the risk to occur. So for example, it would not make sense to add a risk response cost of $10,000 and then say that the cost impact reduction would be $5,000. The only way that would make sense is if I looked at the column L information, which is the estimated risk response probability reduction. This is the column we would use as risk management experts to determine if that risk response would in fact reduce the probability of the risk. So mitigating the probability and not the impact. And as we know, some risk responses will not reduce the probability, will not mitigate the probability. Some risk responses will only mitigate the impact, whereas other risk responses will not mitigate the impact, they will only reduce the probability. And other risk responses will do both. The only way that we should have a negative value here would be if we are also reducing our probability, and therefore we can justify why the estimated cost of the risk response is greater than what the risk would be reduced by as a result of the risk response. So hopefully that's clear. This does not make sense unless we can reduce the probability of the risk. So for example, if we had a 50% probability here, and we reduce our probability by 30%, we may be able to justify to our sponsor why we are spending more money to respond to the risk than what the risk response actually will reduce the risk by, because we can also reduce the probability. So that's just to highlight that, to explain the logic behind that. What else do we have here? We see column J, which is the residual risk cost. And that means that that's the risk that remains after we implement our risk response. It's a calculated formula. It's simply the PERT value, which is column E, minus the estimated risk response cost impact reduction. So the risk that remains after we implement the risk response. The net total risk cost is column K. What is the net total risk cost? Well, it's simply the residual risk. In other words, the risk that remains after that risk response is implemented, plus the cost of the risk response itself. That is also a single point number, deterministic number, which is calculated. So what are we left with? We are left with residual risk probability, which is the probability remaining after implementing a risk response that would mitigate probability, which is calculated simply by column F, our estimated risk probability value, which would be the original input, minus what we believe that particular risk response will reduce or mitigate the probability by. It's calculated for you automatically. Now, the last two columns use distribution functions that are part of at risk. The first one you will see is called simulated occurrence. What does simulated occurrence mean? It means that this particular distribution, which is the Bernoulli distribution, is a very simple distribution that is no different than tossing a coin once, or really any trial that we might do only once. And so this is true to risk events. If risk events are truly individual and distinct between the other risks in a project. The risk itself does have a potential magnitude, a distribution of magnitude. The risk does have a probability. It does have a cost of a risk response, depending on the type of risk response. It may reduce the impact of the risk in terms of the cost, and or may reduce the probability of the risk. Yes, that is all true. However, the risk event itself either happens or it doesn't. We either get a terrorist attack or we don't. We either have system issues or we don't. We either have a delay in the project or we don't. And therefore, the Bernoulli distribution is entirely applicable to specific risk events. And it is simply between 0, the risk does not occur, and 1, the risk does occur. The Bernoulli distribution is based off the probability. The probability is based off of the residual risk probability. So you will see that it is linked with the residual risk probability. In other words, the risk that remains after we implement a risk response. And from there, the Bernoulli distribution is calculated. These also appear to be deterministic. And as you'll see in a moment, in reality, it is going to use random inputs in order to create deterministic values which change throughout the model, the simulation. So you will see that in a moment. It will make more sense once we move on to the example. The last one is then simply the simulated total risk cost, column O, which is simply column N, which is our binary or Bernoulli distribution between 0, it didn't happen, and 1, it did happen, times the total net risk cost. What this model is doing is saying to us, therefore, in this cell, it is saying to us, the question is, in the simulation, when we run a simulation and which simulates the project actually occurring and therefore the risks occurring, some risks over here in this list will occur. Other risks will not. And we can run a simulation once or twice or 100 times or 1,000 times or millions of times. And each time we run it, we will have different outcomes. Some risks will occur, which we'll show here between 1 and 0. And then the next question is, after we determine which risks occur, then we have to determine how significant or how much of an impact the risk actually was, which is measured by column K. So that explains the model itself. And in the next video, I will explain how the model works, and we will run the simulation using an example of a risk register.